Hi everybody, hope you're doing well. This lecture, Fermi gas continued. First, we will discuss the degeneracy pressure, which is a pressure stabilizing matter against collapse. Because if you take the calculation seriously, you'll see that the Coulomb attractions between electrons and the positively charged background exceeds the Coulomb repulsions between the positive charges in the background and the electrons. Uh, so you would have a collapse. All the condensed matter would collapse into a nucleus. Okay, but that doesn't happen because of the Pauli exclusion principle. It was demonstrated that the fundamental aspect providing stabilization for matter which do not collapse into a single point is a quantum mechanical effect which is denominated the degeneracy pressure, which we will calculate for the Fermi gas. So it was demonstrated by Freeman Dyson, okay, originally in the 1950s, I guess, right? He's a very important uh, theorist for quantum field theories. But pressure from the thermodynamic viewpoint is calculated by the following formula. It is the derivative of the total energy of the system with respect to the volume. And the total energy we saw previously in the previous lecture, it is the volume times the integral of the density of states times the energy over the energy. I am assuming here temperature T equal to 0 and corrections at small temperatures are of order T squared. Okay, so the square of the temperature are the corrections to the total energy of the system. But we are interested in the pressure, and the leading order here is the zero order in temperature. Okay, so there are corrections according to temperature. And remember, the Fermi energy corresponds to h bar squared divided by 2 times the mass, the effective mass of the particles, the Fermi wave number squared. And this Fermi wave number, we have shown that it is proportional to the density of the gas to the 1/3. Remember, density is the total number of particles divided by the volume. So volume appears here and appears in the definition of the Fermi energy itself. Okay, so it's very important to take note of that fact because here we need to calculate the derivative. All right, and this G0 here, this is a constant which for 3 dimensions we already shown that this is 2 pi squared, and here's twice the effective mass divided by h bar squared to the 3/2. We will not write it explicitly all the time as just a constant given the mass, Planck's constant, and so on. Okay, so we already have calculated the total energy. It will correspond to an integral over the energies. So you have volume, you have the G0, okay, because you need to insert that. And you have an integral of the energy to 3/2. So you have the Fermi energy to 5/2 and a factor of 2/5 here, okay? Therefore, if you insert here the Fermi energy expressed by this formula here, you'll find out that the total energy of your system will be given by 2/5 of this G naught here, and inserting the Planck constant and mass, everything, you'll find that this will be elevated to the 5/2 power. Okay, this G0 is already there, and if you calculate the Fermi elevated or uh, exponentiated to 5/2, this square here is eliminated, and you have expressing the Fermi wave vector or wave number in terms of the density. It will produce 3 pi squared the total number of particles divided by the volume, okay, to this 5 years multiplying to 1/3, and we have a square here. It gets it produces a 5/3. All right, so this is the total energy of the Fermi gas. And now we can, sorry, it's missing. There's a missing factor here. It's V here. So we can see that the pressure or the total energy of the Fermi gas will be given by 2/5 of G0, which is a constant, this h bar over 2 times the mass, the effective mass, to 5 halves, because it comes from the Fermi energy here, and 3 pi squared times n, the total number of particles, a volume, and a volume to the 5/3. Here you need to just write it as 1 minus 5/3. Okay, so 1 minus 5/3. You see that the total energy goes like the volume to the minus 2/3. Okay, 2/3. Right, this is the dependence of the energy with respect to the volume. And now you can calculate a pressure. Notice that for an ideal gas, ideal classical gas, you have pressure times volume is equal to some uh, number of particles, some constant here, which is a numerical factor here. Number of particles, I guess here is the Boltzmann constant, okay, the number of particles, the Boltzmann constant times the temperature, and for T equal to 0, you get pressure equals 0 for an ideal gas. Okay, there are no pressure for temperature tending to 0 in an ideal classical gas. But for a quantum mechanical gas, temperature can be 0, and because of the Pauli exclusion principle, you cannot put all the particles in the lowest state of energy, and you need to satisfy the Pauli exclusion, and therefore there is an energy here which is non-vanishing energy, and it depends on the volume, which produces a pressure. According to thermodynamics, it is the derivative of the energy with respect to volume, and in this case you will find 2/5. A minus compensates that factor. You'll have a minus 2/3. Okay, but this minus is cancelled. All right, and now you have G0 h bar squared divided by twice the effective mass of the electrons, 5/2 here, 3 pi squared times the total number of particles here is exponentiated to 5/3. I was forgetting this fact here. Okay, so 5/3. And when you differentiate, you need to subtract a factor of 1 here. Okay, so you'll have a minus 2/3 minus 1, which produces minus 5/3, and therefore you can already divide this by 5/3. Okay, volume to the 5/3, and therefore the pressure is some numerical value here. It is it is depending on the density of the gas, but is non-vanishing. You have a finite value for the pressure of the gas. All right, you cannot eliminate uh, by no means you can set the pressure to be zero. This is called the degeneracy pressure. It stabilizes the matter because if no degeneracy pressure, no pressure forces, all matter because of the attraction, which is it is more the value is higher than the repulsion between equal charges. Matter would collapse to a point, but this pressure prevents that from occurring. Okay, so of course you could put again here factors of the G0 and work here. This is again the Fermi uh, the Fermi value here. So it doesn't you could put it as 4 to 15 here if I'm not missing any possible value here. A G0, this is the Fermi, again, the Fermi h bar square, twice the mass square to the 5/2 here, and this is the Fermi constant, the Fermi wave number to the 5th power, which you could write this here as 5/2 of k Fermi squared, and this is the Fermi energy again. But it is just a set of constants, of course. Therefore, this is what you have. Okay. Perhaps I'm um, take a careful look here. I think I am not missing anything, but it seems quite correct. Okay. And this pressure is the stabilizing factor for matter. So Fermi gas, even at temperature equal to zero, has a non-vanishing pressure. It's a very important aspect of quantum matter to be precise. Okay, so quantum effects produce a non-vanishing temperature even if a non-vanishing pressure even if temperature go to zero. Well, now let us turn our attention to spin aspects and magnetization. Magnetization, it is called Pauli paramagnetism. There are two concurrent aspects. One is the spin alignment to a given magnetic field, and the other is the diamagnetic effect, which was studied previously by Landau. So there are two concurrent effects. Spin alignment to the magnetic field, and a diamagnetic effect, which was calculated by Lev Landau. Okay, we will try to consider those aspects when calculating the total magnetization. Okay, so the energy for a free particle in the presence of a magnetic field, if you have a magnetic field, you can write the energy as h bar squared, the wave number squared, divided by twice the effective mass of the electron gas. And supposing an electron gas could be a whole gas, or it could be whatever the fermions are. If they have a magnetic dipole moment intrinsic, you will have a Bohr magneton. The Bohr magneton corresponds here to the electric charge in modulus h bar divided by twice the mass of the particle. This aspect here, really, the mass which enters the Bohr magneton usually is the vacuum mass of the electron, or the electron of the mass of the electron in vacuum. You usually don't account for lattice effects, but eventually you could correct for a G factor here, a correction of G factor. But whatever, I am using here this Bohr magneton to simplify notation, and this is multiplied by the spin times magnetic field B. Okay, it is another one has another aspect to be precise. When you are calculating a momentum in the presence of magnetic fields, one need to include a vector, a magnetic potential vector. Okay, so this is magnetic potential vector. It's an electromagnetic vector for including magnetic interactions. Therefore, the h bar k should be replaced by h bar k minus the charge of the particle. In general, you can have a charge here, okay, minus the charge of the particle times the potential, the magnetic potential vector, okay. And this A here, if you have a field, you calculate a magnetic field by a rotation of this potential, a rotational, the cross product between the nabla and A, the curl of A corresponds to magnetic field. But if you have a static field in the z direction for B equals to some B in the z direction, the field is oriented towards the positive sense of the z-axis. This vector can be written in non-symmetrical form as some B times y in the x direction. Okay, so or if you prefer, I am not worrying about the sign here, or if you prefer, b times x in the y-axis here, okay? Because the derivative with respect to x coming from this nabla operator operating on that will produce the factor b, and x cross product with the y produces the proper uh, field in the z direction. Okay, so you can have something like that. And therefore, for the total energy, you would have something like this: h bar squared k squared divided by twice the mass. There is a orbital angular momentum interaction with the magnetic field, but I am just neglecting that for a while. You'll have a Bohr Magneton, the spin of the particle times b, and you'll have a plus here, e squared divided by twice the mass here, twice the mass, and b x squared. You have a potential energy which resembles the potential energy of a harmonic oscillator. And Lev Landau solved for the quantization of the orbits with respect to this factor here, this x squared here. If you square the momentum in replacement of h bar k, if you replace this h bar k by that factor here, you will see that you'll find a square of this e times a, and e times a produces e squared, the b will be squared, and the x will be squared, and this is divided by twice the mass. As you can see, you could rewrite this factor here as a Bohr Magneton, um, and some other constants here, but this just introduces a diamagnetic effect, diamagnetic term. Okay, this intuitively you can think that when you pick a coil with a current circulating on that coil, and you introduce that coil in a magnetic field, think of the orbital momentum or of the electrons. They are just like coils of electric current, and they, when they align to a magnetic field, the current produce a contrary, a field, a additional magnetic field which is contrary to the applied field, and this is the diamagnetic effect here, and it needs to be taken into account. Okay, but this is just for a single particle is just like a harmonic oscillator potential in the presence of a magnetic field. As I mentioned, Lev Landau solved that problem and found the so-called Landau orbits. Okay, so you need to take into account for the Fermi gas, you need to take into account the spin and the diamagnetic effect. For the sake of simplicity, let me just calculate for the spin, and I will provide the value for the diamagnetic effect, because it is a minus 1/3 of the Pauli effect, and you can correct for the result just taking into account this diamagnetic effect. So for now, just consider the following. Suppose electrons have energies given by a free particle energy. Okay, so this is the free particle energy plus the Bohr magneton. Here is a plus if the charge is negative, as the case for electrons, but it is a minus for holes, for instance, times the spin projection over the z direction times magnetic field applied to the z direction. This sigma here can take only two possibles, plus and minus, corresponding to up spin and down spin with respect to the direction of the magnetic field. So, as you can see, the minus here is favored because it introduces a lower energy state. All right. Now, if you remember quite properly, you need to calculate the density of states. The density of states now will depend on spin. Okay. If you want to calculate now for the spins, the density of states will depend on spin. Okay, so the energy is depending on spin, and you'll have a density of states depending on spins. Okay, because now spin plays a fundamental role, just producing some energy shifts. Okay, and you can see that if you plot the energies with respect to the values of k, the modulus of the wave vector. All right, if you plot the energies here as a function of k, I will I will plot here in this side. K is a modulus, so this side is positive also. But here to this side of the graph, I will plot the up spins and this the down spins for electrons. So remember that the energy depending on k for up spins will be h bar k squared divided by twice the mass, a plus a Bohr Magneton times B. Okay, and for the down spins, depending on k, the energy will be given by h bars k squared divided by 2 times the effective mass minus a Bohr Magneton times B. Right? So there are two distinct energy functions here now. And in this way, if you look at the down spins here, the down spins, I will make the plot here. The energies for k equals to 0 corresponds to minus the Bohr magneton times B. And it is a parabola, of course. All right, this is a parabola. So this is for down spins. For up spins, your parabola for k equals to 0 because it's a kinetic energy term and it's always positive. You start from the Bohr magneton times magnetic field. So you start from here. I am exaggerating this separation here, but for up spins you start here at the Bohr magneton times B. All right? And therefore, if you have a Fermi level here, this is the Fermi level of your system, notice that there are much more up down spins. Okay, this is the population of up spins. They fill all the states till you reach the equilibrium, the new equilibrium Fermi level. And the down spins are now more numerous because it's more advantageous for a particle to be for an electron, of course, because it has a negative charge, to be anti-aligned to the magnetic field. And therefore, you'll have more down spins than up spins. Okay, the population now is unbalanced. If you remove the magnetic field, notice that the populations of up and down spins will be the same. But if you introduce a magnetic field, the two states are split and you cannot use anymore a single density of states for both spins. Only as an approximation you can do that, but for the sake of completeness, the density of states of the up spin is distinct from the down spin. And now just remember that from where it emerges the density of states? It emerges from replacement of summations over k and sigma. Okay, you replace that by integrals over d3k. In the case of 3 dimensions, if you are interested in 2 dimensions, this is a double integral in the area in k space. If it's one-dimensional system, it is just an integral over dk. And of course, you need to insert a normalization factor which corresponds to the volume of the sample divided by 2 pi cubed. In the case of a 3-dimensional system, it will be an area here. So for 2 dimensions would be area over 2 pi squared, integral over d2k, the area in the space, in the reciprocal space. And for 1 dimension, it's L over 2 pi integral over dk. From this, you calculate the densities of states, okay? Because now you want to convert the integrals over k into integrals over the energy possibilities, all right? So the summation of spins cannot be removed anymore. So we need to sum over spins, because previously we just considered that spin is a degeneracy factor of 2 and multiplied everything by 2. Now we want to continue to keep the spin index in the energy labels here, because the energy depends on spin. All right. So let us focus on 3 dimensions. Okay, this is the formula for 3 dimensions. This is for 2 dimensions. This is for 1 dimension. Let us keep the 3-dimensional expression here. All right, so I will erase here. And notice that now this summation would be equal to the volume over 2 pi cubed if you replace this d3k in spherical coordinates, because this is spherical, it has a spherical symmetry in 3 dimensions. You would replace this by 4 pi k squared dk in the momentum space. So you will have 4 pi and an integral over k squared dk. All right, and this we convert all the constants, we move together, and this we convert into an integral over energy, because we can perform a change of variables from k to energy. All right, and this will become a summation over spins, an integral. I'll keep the volume here. Okay, volume times the summation over sigmas over spins of the particles, a density of states for that spin. It now differs from one spin to the other, and it is integrated over energy. So I need to make a change variable here, for which the integral over dk is replaced by an integral over energy, because the two variables are connected to each other. Okay, this energy here, this energy is this form factor, this form of the energy. Okay, but just we now omit the dependence on k, because we are integrating out everything. All right, and therefore what we have, let me erase this here. What we have the following. So for k squared 4 pi divided by 2 pi cubed, okay, 2 pi cubed, 4 pi k squared dk, to become g of the energy integrated over d, we need to make the following identification. We can here we can multiply here by dE over dk. Okay, this is what we are doing, or to be precise, we multiply here by dE, sorry, dE over dE, because I need to multiply by 1. It is equal to G of E times dE. And now, if we pick this thing, all this thing here, this is decay depending on sigma now. Okay, this depends on sigma. And this is the density of states for that spin. All right. And now what we have is an identification with densities of states. G sigma of epsilon is equal to A4 here cancels the 8 here. We have 1/2 pi squared. Okay, this 4 pi divided by 8 is 1/2 pi squared k squared. Sorry, this k squared was already there. 4 pi k squared. I don't need to write it twice. Okay, 1 over 2 pi k squared, and the dk over the epsilon, I can rewrite this as I can rewrite it as d epsilon over dk. So this is the density of states. Now I pick up the energies for the spin sigma and calculate, differentiate with respect to k, introduce the k for that given spin, and I can calculate the density of states here. So any summation will be replaced by this thing here. Volume times the summation over spins and the integral over energy, but the density of states now will depend on the particular spin of the particles. All right, so we can calculate that. Keep that in mind. Now, if we want to calculate for the spin up or the spin down, remember the derivative of the energy with respect to k produces for the given spin produces simply h bar squared k divided by m effective. Okay, the effective mass. This does not stand for complex conjugate mass. Is a real number. So the factor of 2 cancel out here. This factor of 2 coming from the derivative. So for 3 dimensions, we have, when we replace the derivative into the density of states, we find that the density of states given the energy corresponds to 1 over 2 pi squared k squared divided by h bar squared k over m. Okay, this k depends on the spin now. If you just try to calculate k given the energy and given the spin, the k will depend for the same values of energy and b, the k will depend on spin. All right. So this is what we have. And now k of sigma, look at that equation. K squared, depending on the choice of spin, will be calculated according to twice the effective mass divided by the Planck constant squared times the energy for that spin, which we in the notation use just the energy, and this plus Bohr Magneton times sigma times b. When we move to the side of the energy, will change sign, and therefore will be written this way. Okay. Now we can notice that one of the k's here cancel out, and we need to just replace k by its representation in terms of the energy. Therefore, it just produces a factor, a displacement of the density of states. As we have to have that because we already know that the energy shifts according to the applied magnetic fields, and the shift is distinct from the up and down spins. Okay, so 1 over 2 pi squared, the square root of twice the mass h bar squared, but here we have a inverting that factor m divided by h bar squared. We can multiply by 2 here if we divide by 2, so we get a factor of 4 here. These 2 cancel this 4 and produce this factor of 2 here. And now we have to replace the k, this comes from k, by energy minus Bohr Magneton times sigma times b. Right? And therefore the 3 halves we regain that factor. So the G sigma of epsilon corresponds to 1 over 4 pi squared twice the effective mass of the particles to the 3 halves here, to the 3 halves, times a energy which now, or times the square root of the energy which now is being shifted by the application of a magnetic field. All right, so this is the density of states depending on magnetic fields. And in general, a very general scenario, in general, if you have the following: energy is equal to h bar squared k squared divided by twice the an effective mass plus some delta. This delta is some shift in the energy scale, or you can plug in here some E naught. All right, this corresponds in three dimensions to the density of states G of epsilon equals to some G0, okay, this is some constant, times the square root of the energy minus that reference level. Okay, so it's very general replacement. Okay, but for our definition, here you could have another constant multiplication. But in our case here, we previously defined that G naught, that G0, to be 1 over 2 pi squared, 2 times the effective mass divided by h squared, h bar squared, to the 3 halves. And therefore, the G, depending on the spin, is equal to G0 over 2. Let me use another G0, some A here, okay? Just for you to not be confused. Because here we have a factor of G0, this G0 over 2, and times the square root of epsilon minus the Bohr Magneton times B times the sigma. Okay, the sigma is the spin. It can take on 2 possible values. So if we specify for up spins, we have G naught divided by 2, square root of energy minus a Bohr Magneton times B. Okay, this is for the up spin. And for the down spin, we have a G naught divided by 2 is a constant divided by another constant, just a constant. The relevant aspect comes into play here inside this square root. It is the energy. If we have a down spin, it is a minus sign here. Minus times minus is a plus. So plus a Bohr magneton times B. These are the densities of states separated by spin. It is explicitly written in terms of this equation. Notice that if you don't have a magnetic field, two equations coincide, and summation of G up and G down produces G0 square root of E, which we already used previously. Okay, this is it for now. Well, so far so good. We could plot the densities of states against the energy. So if you want to plot the G's, okay, as a function of energy, what would you have? The density of states for up spins needs to start at this value here, because otherwise for energies lower than that value, you'll have a square root of a negative number, which produces a density of states which is a purely imaginary number. It doesn't make sense. So the up spin starts at the Bohr magneton times B, okay, and the down spins starts from here, minus the Bohr magneton times B. So, of course, if you look at now this picture now, and you have the Fermi level here, it is clear that the number of, this is for up spins, okay, it is clear that the down spins are in a major, they are the majority, okay, they are the majority, because the difference between this area and this area here corresponds to the difference between the number of particles with down and up spins. Okay, so now let's turn to the calculation of the magnetization of a Fermi gas, the Pauli paramagnetism here. There is one interesting thing which comes from the Hamiltonian definition. The Hamiltonian is defined as, suppose you define the Hamiltonian the following way: Bohr magneton times the sigma z times a magnetic field. This is for electrons, the spin part. For electrons, spin part. Okay? Or for spin half particles, you have that. Notice that if you calculate the derivative of the Hamiltonian with respect to the B field, you'll find Bohr magneton times the Pauli matrix. So this is the operator for the magnetization. If you take the average here of this, you'll take the average of the spins. And now, if you remember, this is for just one particle. The magnetization, the total magnetization is the total number of particles divided by the volume of your sample, a Bohr magneton times the average of sigma z. All right? And of course, if you use a second quantized Hamiltonian, you can use this aspect here to demonstrate that Bohr Magneton times this object divided by the volume corresponds to the derivative of a density Hamiltonian with respect to the magnetic field. This produces magnetization. All right, this is the density. This H is the Hamiltonian. This, in another style, is this fashion. H is for Hamiltonian divided by volume. All right. So magnetization in general corresponds to the derivative of this here. But there is a minus sign here because for electrons we have a negative charge. So for instance, if you would have a positive charge, you would have a minus here. And positive charges would produce, in the presence of a magnetic field, spins up in the majority and spins down in the minority. So you need to compensate for a sign. So you need to calculate the negative of the derivative of H with respect to B. This produces a minus here. So for electrons, this minus is uncompensated. And in general, if you want components of magnetization, for instance, a J component, you need to calculate explicit derivatives of the Hamiltonian density with respect to the component J of the magnetic field. Okay, but in this case, we will just use the aspects which we already know. Okay, we will, when you multiply n times the average of the spins, you already are calculating, as a matter of fact, the following: minus the Bohr magneton divided by the volume of the sample. Okay, you are trying to calculate the magnetization in the average. In the average, the z component, because magnetic field is applied to the z direction, this is the magnetization of your sample. It is minus 1 Bohr magneton, because this is the magnetic momentum for one electron, times the number of up spins minus the number of down spins, which can be reversed here because of this minus sign. So Bohr magneton divided by volume, the number of down spins minus the number of up spins in average. This is the average of the operators. Okay. Therefore, you need to calculate this object here. Just remember, I will write the equation here. The magnetization corresponds to Bohr magneton divided by volume, the number of up, the number of down minus the number of up spins. All right, this is what you have here. Okay, so for a given spin, for a given population and sigma, we need to calculate the summation over k, not over sigma anymore, just over k of c dagger k for that spin, c k for that spin. Remember that no matter what, n up plus n down, applied magnetic field or not applied, if you have or don't have any magnetic field in your system, this number is just what we calculated previously. This is a constant. It doesn't depend, for a closed system, it doesn't depend on temperature or whatever, or applied magnetic field. This is a constant. What you can do is to move some of the up spins into the down state, because in the beginning, if you don't have any magnetic field, the populations are equal. They are the same amount. There are the same amounts of up and down spins. When you apply magnetic field, some up spins migrate to the down spin state, and now you have more down spins than up. But the sum of the populations is a constant. of your problem. So now we need to calculate the n sigma here, the population in the sigma state. It is replaced by an integral over the volume 2 pi cubed, okay, an integral over d3k of the average, because we are taking the averages here. We already demonstrated that this average for fermions produces the Fermi Dirac distribution. Depending on the energy and on the chemical potential at temperatures far from the Fermi temperature of this system. For very high temperatures, things can change, but for the sake of simplicity, is a very good approximation for Pauli paramagnetism. As you can see, next leading order will be in terms of the square of the temperature using Sommerfeld expansion. I will let you to do that as an exercise if you want. If you want to go beyond the first order or the zeroth order approximation in temperature, but in temperatures very smaller than the Fermi temperature, in the thousands of kelvins for metals, you could use an approximation, approximately 1 from any given energy to the Fermi level and 0 above that Fermi level, okay, in terms of energy here. So we are replacing the Fermi level approximately by the chemical potential, or the chemical potential by the Fermi energy, all right? This is an approximation. And therefore, the number of spins would be approximated by volume and integral, because this object here we replace when we pick up together the 1 over 2 pi cubed, 1 over 2 pi cubed, integral over d3k. We replace this by an integral over densities of states given that spin, because for that spin times dE, we are replacing that by an integral over energy. It is possible because your energy states are symmetric. They have spherical symmetry. In the case of the free fermion gas, it is an approximation for a free fermion gas. The density of states doesn't depend on the direction in the k space, all right? So it is symmetrical, spherically symmetric, all right? We have therefore an integral from minus infinity to infinity, or to the Fermi level here, to the Fermi level, or better, because G sigma is just the G0 over 2 square root of the energy minus sigma times Bohr Magneton times magnetic field. Because of that, we start our integral from sigma Bohr Magneton times B. Notice that for up spins, it starts from plus Bohr Magneton times B. And for down spins, it starts from minus the Bohr Magneton times B. And this is the G0. This is the density of states, which we are talking about here. Square root of the energy minus sigma times Bohr Magneton times magnetic field. And therefore, if you replace the Fermi Dirac by 1, till reaching the Fermi level, it's just an integral over energy here. Okay, so this is the number of spins. The particles with that given spin is just an integral, all right? It's just, we just need to integrate that. And therefore, let us calculate these integrals here. It produces nothing but the following: G0 over 2. If you replace the lower limit in these integrands after the integration, you get 0. This is a constant, so G0 over 2 times the volume. This integral just corresponds to the same thing, but to 3 halves, because it's 1 half, and divided by 3 halves. So this factor of 2 cancel out in the end, and therefore we will have n sigma is equal to G0 over 2 times the volume of your sample. Notice that we need to divide the total number by volume, so this volume here will go out of the final result. And in the end, we need to replace the limits. This will become Fermi level here. But now notice the following. Notice the following aspect here. I will erase this, but just remember that fact. We have G0V over 2, 2/3, because this factor 1 over 3/3 is 2/3. It cancels this 2 here, and it becomes a factor of 3. We can, remembering that Fermi energy is much higher than this energy modulus, which doesn't depend on spin now. Okay, so this Fermi energy is it's higher than this thing here. You can plug in some numbers, but this is in the range of 1 to 10 electron volts for metals, for alkali metals mainly. So this is around the range of 5 electron volts, say, and this for high fields, you'll have something in the range of milli electron volts at most, but usually in the range of micro electron volts. So this energy is really, really smaller than the Fermi level. Okay, so we can just factorize the Fermi level here. We will have Fermi level to the 3 halves. Okay, and 1 minus sigma Bohr Magneton times B divided by the Fermi energy to the 3 halves, to the power of 3 halves, right? This allows an approximation given that fact, all right? If we consider that approximation, that fact, we can approximate 1 plus or minus something here, something which is smaller, much smaller than 1 to the power of n is approximate to some power alpha here. It could be anything, it could be a fraction, it could be anything. Okay, if this a is in modulus, the modulus of a is much smaller than the unity, you can approximate that by 1 plus or minus alpha times A. And this way we have G0 times the volume divided by 3, Fermi level to the 3 halves. And here we will have 1 minus 3 halves, 1 minus 3 halves, sigma Bohr Magneton times B, because the exponent is 3 halves here, all right? This is the good approximation, divided by the Fermi level, of course, divided by the Fermi level, all right? It's energy over energy, it's an I-dimensional constant. And notice also the following. From the previous lecture, remember that let us let us continue the calculation. But in the end, we will replace everything by the total number of particles, right? So now we want to calculate the magnetization in the z direction, and we have to calculate the Bohr Magneton divided by volume, the down spins minus the up spins. We have a Bohr Magneton coming from the definition of magnetization divided by volume. And here, what is constant independent of spin? G0, V over 3, Fermi level. So G0 times V divided by this factor of 3, the Fermi level to the 3 halves. Okay. So we have now for the up spin, for the down spin, 1 plus 3 halves of sigma, the Bohr Magneton. Sigma is a plus 1, so a plus 1. 3 halves of the Bohr Magneton times B divided by the Fermi energy. Okay, this is for the minus here for the down spins. The down spins corresponds to sigma equals to minus 1, and the up spin corresponds to plus 1. All right, so if you insert that here and you subtract, you will have minus 1 because it's minus this one, minus, and here you need to insert a plus for the up spins. This minus cancel out, changes sign, so you have a plus 3 halves of Bohr Magneton times B. Okay, so this part here comes from the end down, and this comes from the end up. This minus 1 and this plus 3 halves here. You need to calculate the difference between the populations. Of course, things here cancel out, and you'll find out that the magnetization corresponds to 1 minus 1 is 0. This factor of 3 cancel out. 1 half plus 1 half produces a 1, and the volume cancel. G0 times Fermi energy to the 3 halves times Bohr Magneton squared times B. All right. To be precise, the magnetization for the proper units, all right, it is related to, or the susceptibility is related to the intensity of the magnetic field. Usually you write it as the vacuum or the medium mu, the permeability of the medium times the magnetic field H. So this is the flux, the density flux, or the flux density, magnetic flux density, and this is the intensity. If you are dealing with the international system of units, this is measured in Tesla, and this is measured in ampere per meter. All right. So eventually, you want to rewrite the magnetization using the intensity. So the magnetization, but do not confuse it with the Hamiltonian. So G0 times mu naught times Bohr Magneton squared. You have two mu's here. One is for magnetic permeability of vacuum. This mu naught is 4 pi times 10 to the minus 7 henries per meter in the international system of units. The Fermi energy I will put together with this G naught here times the field intensity, magnetic field intensity here. Okay, so in the end, if you want to calculate the magnetic susceptibility, you need to calculate the following. A magnetic susceptibility is the derivative of the magnetization with respect to the intensity of the magnetic field it produces just the G0 Fermi energy to the 3 halves and mu naught Bohr Magneton squared. But notice that if you want to calculate the total energy of the total number of particles of your system, you would calculate with a factor of 2. You would have a G0 times the integral from 0 to the Fermi level, the square root of the energy here times the, okay, times the volume. So I will divide it by the volume. And this produces G0, the Fermi level to the 3 halves, okay? And it's divided by something here, which is a 3-half factor, okay? And this is just the density of particles. This is the density of particles. So if we want to replace this object here by the density of particles, we will have a 2/3 of the total density of particles, the constant of the magnetic permeability of the vacuum times Bohr Magneton squared. So here also you would have 2/3 of the density, the particle density times mu naught times Bohr Magneton squared. Okay, so this is what you got from these calculations here, right? Well, now if you from this magnetic susceptibility you subtract the diamagnetic effect, it is minus 1/3. It corresponds to minus 1/3 the Pauli factor. All right. So it is this value minus 1/3. You'll find for the Pauli the total magnetic susceptibility a factor of 1/3. So the paramagnetism, the tendency to alignment with the magnetic field, prevails in this case because it's 2/3. If you calculate the diamagnetic effect, you have a minus 1/3 factor. So I have 1/3 the density of particles or the total electron density times the Bohr Magneton squared. And you can calculate that for metals, okay? This is in the range of 10 to the 28 per cubic meter, so meter to the minus 3. This value here is something like in the range of 10 to the minus 6, just to get the order of magnitude, all right? And this value here is on the order of 10 to the minus 23, so squared, 10 to the minus 46, and you can find out the order of magnitude of these values here, okay? Uh, so this is it for Pauli paramagnetism. Uh, Perhaps I'm missing some other constant here, but it is just important aspect to notice. It is constant, nearly constant, almost independent on temperature. Okay, this is a very important issue. When you calculate for spins, a collection of spins, a system of a two-level system, we found out in a previous lecture that for collection of spins, we found something like the magnetization depending on Bohr Magneton times the hyperbolic tangent, Bohr Magneton times B divided by KBT. And if you is properly multiplied by n here, if you take the small temp, the smallness of this aspect here, we would find m approximately divided by b, which produces a susceptibility in the range of density, Bohr magneton squared, and it is divided by kBt. So this is C, a constant divided by temperature. This susceptibility here, which is the susceptibility of a collection of spins, 1/2 spins, okay? Compared to the Pauli paramagnetism, you can see this depends on 1 over the temperature, and this is almost constant in temperature. The Pauli paramagnetism for a Fermi gas will produce that result only for very high temperatures. This is a result for high temperature. Remember that for small temperatures, we can go to square of the temperature as the leading order correction, but you are considering that the temperature of your system is very well below the Fermi temperature. Here, besides the fact that here is just considered a system of two levels, of spin levels, it doesn't take into account the fermionic aspect of your problem, but this just produces anything valid for high temperatures. You cannot apply this directly to the Fermi gas, okay? And this is the Curie law for the magnetic susceptibility. So you would have something like this, a constant over a wide range of temperatures, and then only then it will decrease as 1 over T. So for low temperatures here, it is just falling as for low temperatures, it will fall like this, the square of the temperature if you would calculate a Sommerfeld expansion. It's tricky to calculate this thing here, okay? But for very high temperatures, the Pauli paramagnetism, you could replace the 1 over beta E minus mu plus 1 over that factor, by a factor of 1 over minus beta times the energy, and in this case, high temperatures, you would replace by this function by something like this, and perhaps the results would coincide in the form because it will have a temperature dependence depending on 1 over T, okay? So this is for the Pauli magnetism. It is nearly constant, the response of a Pauli metal, the response of a Pauli metal to an applied magnetic field to the leading order, to the zero order in temperature, it is a constant. But if you allow a temperature correction, it will be the leading order correction will be on T squared, okay, because of the Sommerfeld expansion. And it will only tend to a Curie law only for very, very high temperatures. Okay. Now, to finish this, let us consider the electronic transport or conductivity. Okay, electrical conductivity of the electron gas. The proper calculation cannot be done in the context of a free electron gas purely because you need to include needs to include lattice vibrations, at least. Okay, these lattice vibrations go, when quantized, by the name of phonons. The quanta of the lattice vibrations, the background of positively charged ions, they jiggle around the equilibrium position a little bit, and they produce waves, sound waves in the medium, and these waves change a little bit the background potential. The electron feels it, and it will be scattered by these vibrations. Okay, so electrons will, suppose an electron is going here and there is a positive charge. The positive charge moves upwards here. The electron feels a, a pull and will be scattered right to that, to some angle here. It will be scattered by the motion of this lattice ion. You could see it another way. Suppose there is something which at temperature T equals to 0 is it is nearly static, but and the electrons or something moves along its side here. If it moves, it is a target which increases the cross section and scattering increases. Okay, so scattering rate increases with temperature. Okay, this is a very important aspect. You would have a scattering rate, a collision rate, collisions per second. This by some function, it depends on the phonon spectrum and the dimensionality of your problem. This rate of collision, which is a proportional, let me use a nu here, it is inversely proportional to a collisional time. So this is a average collision time, a collision or relaxation time. Let me use this. Okay, this time will be decreased. If you increase temperature, this time decreases. All right. So the whole Fermi sphere, if you want to calculate kx, ky, kz, for now, suppose magnetic field is 0, you could calculate everything with magnetic fields. Okay, magnetoresistance, there is a problem which is very important in physics and materials science nowadays, which is an electrical engineering, which is magnetoresistance of materials. For a very long time, it's a very important problem. But if you consider this, the Fermi sphere, it goes to the K Fermi here, the modulus of the wave vectors, the wave number of a Fermi energy. Okay, all the electrons are here, but for each electron in one direction, you have an electron moving in the opposite directions. This is K, this is minus K. Okay, so if you want to calculate the current density, you need to calculate, this is the electrical current density, you need to calculate the following: the average of the velocity operator, okay, the average of the velocity operator times n particles divided by the volume, right? Something like this. Of course, it is times the electric charge of the particle. So charge, number of particles divided by volume, and this is the velocity operator, the average of the velocity operator. But velocity, considering a very crude approximation, velocity operator would be given by momentum divided by mass. In quantum mechanics, this is not always true, but let us consider it to be true, to be okay to use this. And therefore, our momentum corresponds to the following thing here. H bar k over m, this is our velocity operator depending on k. So we need to sum over all the k's, all right? We need to sum all the velocities. We need to sum all the velocities. If we sum all the k's in this problem, we are summing all the electrons here, and this will produce the velocity on the average, okay? The average of the velocity operator, which is related to the electric current here. But notice that for electric field also equal to zero, electric field zero, there are no electric fields. All the energies depend only on k squared divided by twice the effective mass. And in this way, if you sum over all the velocities of particles, if we sum over all the possible velocities of the particles, we will have zero. Why is that? Just because for a given k pointing upwards, there is a k pointing downwards. And for any k, there is a minus k inside the Fermi sphere. Okay, so there is a total cancellation of the wave vectors. So the velocity for non-applied electric fields is zero. The Fermi surface doesn't move. Okay, this is very intuitive. No applied field, no electric current. So J for E equal to zero produces nothing, produces zero. There is no current, no electric current. Okay? But if we apply an electric field to our problem, what do we have? The derivative of momentum with respect to time. Okay, this is Newton's second law. For quantum mechanics, it is valid in the correspondence limit when you take averages of things. We are calculating averages here. And in this case, you could show it properly, but we need now to introduce a factor here. I will explain it in a moment. For Newton's second law here, we have the derivative of momentum with respect to the time is equal to the electric charge times the electric field. This is the electric force. If you have magnetic fields, you need to take into account the magnetic forces also. But there is a phenomenological dissipative term. And this dissipative term corresponds to if no applied electric fields, a given thermally activated electron must relax to its original state within a certain amount of time, which is associated with collisions. Okay, this is the Drude model. So this is Drude model. All right. But now, for our problem here, we would have in the stationary case, we would have to solve this. So this is included by hand. We would find that P or delta P, okay, because this is just a slight correction to the momentum, and this is the total momentum, but the total momentum for no applied field is zero, so this is just a correction. It's just a correction. This delta P, which is a correction for all the momenta of the particles, corresponds to tau times the electric charge times the electric field. Okay, so it is dependent on the electric field and dependent on the collision rate. An electron can gain some energy, but as soon as it scatters, it is pushed back to its previous state. Okay, in the Drude model. So it is related to the Drude model of conductivity. Here we are just mixing some aspects of quantum mechanics and some aspects of a classical model, but the delta of momentum corresponds to h bar delta k, h bar delta k, divided by mass, or multiplied by the effective mass, because, sorry, it is not divided by anything here. It is just that the delta of momentum is h bar delta of the wave number, which is equal to time, the collisional time, multiplying charge, multiplying the electric field here. And of course, we can calculate delta K, which is a constant. The charge times tau times the electric field divided by h bar. Okay, so this is the dislocation of an electron in the Fermi sphere. In other hands, or in another way to put it, in another way, you have the Fermi sphere centered at the origin. If you have electrons, you introduce an electric field in that direction. Okay, if electrons, the Fermi sphere will entirely, because this delta k is not dependent on the value of k in the static case, in the stationary solution for which the derivative is zero. So we have this equal to zero. Okay, and the new center will be this delta k here. The entire sphere dislocates. It doesn't contract or expand. My picture here is a little, so to be precise, the size of the Fermi sphere doesn't change. It just dislocates because they are electrons. They are dislocated by some delta k. And this delta k corresponds to exactly minus, for electrons, the charge is minus E. Minus E, the collisional time times the electric field divided by h bar. So the Fermi sphere is displaced by some amount, delta k. All the momenta are displaced by this factor. This way, our velocity operator, which corresponds to h bar k over the effective mass, now if you sum over all the allowed values of k, the original values produces zero, but now the average velocity produces something like summation over all the values of k of the same amount, minus E times tau times the electric field divided by h bar. Divided by, sorry, it's h bar times the delta k, which is minus E times tau times E divided by the mass of the particle, because it's velocity. So it's a delta k. And this case now for applied field is the original, centered at the origin, plus for any k, we have the same amount of dislocation. So in entire Fermi sphere is displaced now. And therefore, summing over all the case produces just, you could think that a momentum operator, to be precise, would be replaced by h bar k, c dagger k, c k. Okay, this is the proper definition, but this is in the average. You pick the average here, the average here, so you have a delta k for all the k's times the h bar times the average c dagger summed over all the k's, c dagger over all the spins, it doesn't depend on spin in this case because you are not applying magnetic fields. So if you take that, this is just the total number of particles in your system. And now you can calculate the current. The electric current corresponds to that momentum, velocity of the particle, times charge, which is minus E, and divided by the volume, a summation over all the momentum of your system, and divide by V, divide by the mass, the effective mass. Okay? And in this case, of course, you'll find out that the velocity operator, if you write everything in place, this is just the number of particles divided by volume. It is just the density of particles. You need to replace here by some delta k, which corresponds to e squared, because you have minus e coming from here and minus e coming from here, e squared tau divided by effective mass, so it's the velocity. Okay, this is just the total number divided by the volume, the charge minus e times the average velocity. This is current density, charge density times velocity in classical terms here. And therefore you have the following relation. Okay, you replace velocity, minus e times minus e doesn't depend on the sign of the charge. And this is the electrical conductivity. This is Ohm's law. Okay, this is Ohm's law. The density current, it depends on the applied electric field times a constant, this constant, which is not in general a constant, but in a metal, for low frequencies of the applied electric field, it is nearly constant. Okay, this constant here is called the electrical conductivity. Electrical conductivity, and is measured in Siemens per meter, or ohm to the minus 1, meter to the minus 1. And notice the value here for the electric conductivity. It depends on the total number of allowed or free electrons in the gas. And this total number we already calculated, is just the N divided by the volume. All right? It depends on the fundamental constant, which is the electronic charge. It depends on the effective mass. This effective mass you only can calculate if you consider the exact form, or at least an approximated form, of the background potential, and you try to remove the interactions of the electron with the background potential, but the electron with the original mass, you need to calculate the corrections of the mass to the effective mass. So this is a quantum mechanical effect here for the mass. The quantum mechanics is in the mass, the effective mass. Here are quantum corrections to the mass. And of course, there are effects, quantum mechanical effects on this object here, the collisional time. Okay, this depends on phonons, on vibrations of the lattice, and this is a Bose gas in a very, the phonons can be very crudely approximated by Bose gas of spin zero particles. They interact with electrons, and these interactions introduce the collisional rate or interaction. You need to calculate these interactions to calculate the collisional rate and to calculate this tau here. But just remember that the phonons are bosons, and therefore they follow Bose-Einstein statistics. So this depends on number of phonons. The higher the number of phonons, increasing number of phonons, of course, tau decreases. And the number of phonons depend on something like 1 over the beta, which is temperature, times h bar, the energy of the phonon, minus 1. So this introduces a temperature dependence, which eventually could be exponential. So the conductivity, this tau here, is something like tau 0 e to the minus some function of temperature minus beta e naught or something like that. But of course, for if you increase the temperature of your system, the conductivity will be lower. But of course, in the case of semiconductors, you could apply a Fermi gas approximation, but there you need to take into account the hole and electron separatedly and then introduce interactions, because you could promote electrons from the valence band to the conduction band, and this will increase the number of charge carriers in your system. And therefore, looking just to something like this expression here, this expression is very good approximation for metals. Okay, it could be used for other things, but for metals, if you increase the number or if you increase the temperature, you only act on you are only acting on the collisional time. So for metals, the conductivity as a function of temperature will decrease. Okay, conductivity, and eventually for some specific cases, you have superconductivity, and this way, at a given critical temperature, this conductivity goes to infinity and starts to become infinite. But its critical temperature is a few Kelvin for most of the metals. In general, for usual temperatures, if you increase temperature, conductivity decreases, all right, for a good metal. But for semiconductors, you have a distinct behavior, because if you increase temperature, of course, collision rate increases. But there is another effect, which is the promotion of electrons from one band or one energy band to the other, and you create carriers. The effect of temperature is non-conserving the total number of carriers. For a metal in a well-defined volume, or even if the volume changes, the density could change, but there is a slight modification. This number is already in the range of 10 to the 28, 10 to the 29, And for semiconductors at very small temperatures, this number here of carriers, charge carriers, is around 10 to the minus 11, 10 to the minus 12, 10 to the minus 15, to plus 15, to plus 12, okay? 10 to the, but 10 to 10 to 12 orders of magnitude smaller. So for metals, this N for metal is around 10 to the 29 per cubic meter. And for semiconductors, at very small temperatures, for zero, for instance, it would be zero, ideally. But for some given temperature, it is small temperature, small temperature. It is in the range of 10 to the 10, 10 to the 14. So the doping acts on this number, the number of carriers, the total number of particles in your Fermi gas. But temperature, because of the interactions between holes and electrons in the semiconductor, it temperature can increase the number of carriers. You can, by thermal activation of your carriers, you can increase this number. And for a semiconductor, the number of carriers increasing with temperature is a much more pronounced effect than the increase of the collisional rate, which produces a decrease in the time between successive collisions. So for a semiconductor, the behavior is quite distinct. It increases, the conductivity increases with temperature. So for semiconductors, increase with temperature. The most of the effect is in the density of charge carriers. And for metals, the number is nearly a constant. You're not promoting those core electrons in the ions in the background to the conduction band. You just need to work with the Fermi gas with free electrons, which were already there. Okay, for semiconductors, a distinct picture. You can move electrons from above a energy gap from one energy band to the next one, and this is promoted by temperature. And temperature has let me say, um, a good action for the conductivity of semiconductors. So for intrinsic semiconductors, okay, so this is the intrinsic case. For intrinsic semiconductors, conductivity is increasing, okay? But so far, so good. For the Fermi gas, I think we already done. In the next lectures, we will discuss some aspects of bosons, and I'll see you next time. Bye bye.